So great to see you here. Yeah, this meeting being live streamed. So welcome everybody to this ICLP 2021 invited talk session. It's my great pleasure to introduce Professor Stuart Russell from UC Berkeley, where he's a professor in computer science and also the Smith Zett Chair in Engineering and Director of Center for Human Compatible AI. And I usually don't read these, but some I do because I'm sure he has so many words besides these like Ichika, computers, and thought words. He held this Pascal Chair in Paris, which are usually given to international, not usually, I mean, always given to internationally acclaimed influential scientists. And just this year, he received the OBE from Her Majesty Queen Elizabeth. I had to look up, but that's the most excellent order of the British Empire. And Professor Russell is an honorary fellow of the Wadham College in Oxford and Andrew Carnegie Fellow, and these fellows, ACM, American Association for AI, and all that. And his book, his textbook, AI, okay, Our Modern Approach with Peter Norvig, is the standard textbook for AI used in 1,500 universities in 135 countries. I can say myself, 18 years ago, when I was looking for a AI textbook to teach from, this was just way stand up. And by now I thought probably 10 different subject and book areas I was searching for. This is still above all those areas I've seen. And Professor Stewart's research covers a wide range of topics in AI with a current emphasis on long-term future of AI and its relation to humanity. He has developed a new global seismic monitoring system for the Nuclear Test Ban Treaty, and is currently working to ban lethal autonomous weapon. Please, Professor Russell.
Thank you very much, Annie. It's a delight to be here. I'm really sorry I can't, well, I'm sure we're all sorry we can't be at the conference in person, but hopefully that will happen soon. So I'm going to share my slides. And so I'm going to talk about work. Some of you may have seen this before, but there's always a wrinkle here and there. And for some of you, it'll be new. And it's something I've been working on, I suppose, since the mid-'80s, towards the end of my time as a graduate student, which I see Ben Grossoff in the audience. He'll remember that time. Let me start. So I'm going to start with a sort of a complaint about the way the world is right now. So we've all seen these really big events like the defeat of Lee Sedol, one of the world's great Go players, by AlphaGo. That's certainly a significant event, although it's notable that AlphaGo uses about 10 to the power of 13 times as much computation as Arthur Samuel's checker playing program, which didn't quite reach world champion level, but did get a draw with the world champion back in the early 1960s. And I think one of the things that's been lost in the current excitement about deep learning is something that the logic programming community has been aware of for decades, and particularly the inductive logic programming community, which is expressive power. And the key point is, if you use an inexpressive language, such as feed-forward circuits, then for some functions, you are bound to end up with very large function representations, which means you get very little generalization and very slow learning. And we can illustrate this just by looking at the rules of chess, which is a very, very simple game. It's discrete time, discrete space, very small number of objects. But if you try to write down the rules of chess in an inexpressive language, such as a finite automaton or a hidden Markov model, it would be about this many pages, so 10 to the 38 pages, just to write down the rules of chess. If you do it and that's basically because the states are completely uninterpreted board positions treated as atoms. And so you don't capture any of the regularities in the rules whatsoever. If you try to write it in propositional logic, or circuits or Bayes nets, graphical models, and so on, then you get propositions like the white king is on c4 at move 12, and you have to write a rule for that proposition. Under what circumstances does it hold? And you have to write a rule for every such proposition. It ends up being about 100,000 pages. And again, you're failing to capture the regularities that hold in the universe. In first order logic, it's about 1 page, and you just write rules defining when is a piece of a particular color on a square at a time. And you can do that because first order logic breaks up the proposition symbol into predicates and arguments and can quantify the arguments. And that allows it to capture a lot of the regularities. In fact, as far as I can tell, all the regularities that exist in the rules of chess can be captured by first order logic. So standing back, it's all about capturing regularities. Right? And that's really all that matters here, right? The universe has lots of regularity. If you can't capture it, you can't learn. And the same problem is going to happen actually for any language where the decision problem, for example, running the classifier on a new example, if that's a linear time operation, then it's not going to be able to efficiently represent anything except for linear time languages. So I think we're in danger of actually repeating history in a slightly different way. So what I'm going to call bad old-fashioned AI, not good old-fashioned AI, but bad old-fashioned AI. There was a period in the 50s and 60s where people ignored computational intractability, partly because they didn't know that it really existed. There was no theory of NP completeness or anything like that. They were aware that simple algorithms would have exponential runtime, but most of the high-level discussion about AI assumed that computers are basically infinitely fast, and we don't need to worry about this. I was just looking at a book from 1952 called Faster Than Thought, right? And that's written at a time where a floating point multiply might easily take 25 milliseconds. So you had 40 flops, not 40 kiloflops or gigaflops or petaflops or exaflops, but 40 flops. And they thought that was faster than thought. And deep learning is, I think, doing the same thing, except with respect to sample intractability. And I see this with the grad students in my class. If you point out, well, it's learning incredibly slowly, they'll just say, oh, don't worry, we'll just collect more training data, right? And that might mean 1,000 times more, or 1,000,000 times more, 1 billion times more. And that clearly it just doesn't work in the long run. The universe doesn't contain nearly enough training data for a deep learning system as we currently understand them to really become intelligent. And I think some people in the community are realizing this, not all, but Francois Chollet is one of the leading exponents and built one of the main deep learning packages. And in his book, which is a pretty good book about deep learning, says many more applications are completely out of reach for current deep learning techniques, even given vast amounts of human annotated data. So you have to give him credit for acknowledging that. And then he goes on to say, the main directions in which I see promise are models closer to general purpose computer programs. And I don't think he's being sort of ironic here or anything like that. I think he wasn't aware that people have been working with models closer to general purpose computer programs. Now, certainly in inductive logic programming for getting on almost 40 years, and in probabilistic programming, 24 years now. So I'm going to talk about some of these models closer to general purpose computer programs. So let me try to summarize the history in a cartoon, right? So go back to 1950 odd, where we're trying to build AI systems for the real world. And I think people like John McCarthy recognized that the world has things in it, objects. If if you looked around at that time and said, okay, what mathematical tools do we have that can handle worlds with objects, right? Well, if you talk to the applied mathematicians, they had dynamical systems, which had vectors, but not really objects, right? So you could represent the state of the world as a vector. If you talk to the statisticians, you had linear regression, you had mixtures of Gaussians, right? Neither of those are going to help you do the shopping at the supermarket. And this is the kind of example that people in AI would like to be able to address. And so they did not see solutions in the mathematical formalisms that were available, except for mathematical logic. So, so John McCarthy and others said, the world has things in it, and so we need to use something like first order logic. And now, for some reason, my screen. Okay, there we go. On the other hand, another group of people recognized that the world is uncertain, and pretty much a disjoint group of people, I would say, until later on. And so we saw, for example, the development of Bayes nets to handle that. And this took quite a bit longer. There wasn't really a good formalism for representing probability, even at the sort of propositional level, until Udo Perl and others in late 70s, early 80s started to develop what we now call Bayes nets. And that led to a bit of a revolution in AI. But of course, eventually, both groups realized what the other group already knew. So the logic people realized that, okay, fine, the world is uncertain. And the Bayes net people said, okay, the world has things in it. So people started working on first order probabilistic languages. And I'd say, Joe Halpern in the late 80s, early 90s, David Poole, and a number of other people, Taisuke Sato in Japan, and so on. And I'll talk about a little bit of that history. But there's something else that happens when you put these two things together, which is that the world has unknown things in it, right? If you have uncertainty, it's not just about the properties of the objects and the relationships among the objects. It's about the existence of the objects and the identity of the objects. And that type of uncertainty wasn't considered in the early generations of first order probabilistic languages. And when you add that in, you get what I've been calling open universe probability models, or first order open universe probabilistic languages, if it's a bit of a mouthful. And this makes a big difference. There are many, many applications for which you don't know a priori what objects exist. For example, in computer vision, until you open your eyes, you don't know what objects you're going to see. When you read a book, before you've read it, you don't know who the people are that the book talks about. And if you read a Russian novel, you will never figure out which person is which. So, so going back and looking a little bit at some of the key steps in the development. So I think it's reasonable to say that although various people, including Boole himself, said, we would really like to have some combination of probability and a general expressive logic. Chaim Geifman's paper, 1964, was the first that I'm aware of to make a really concrete step towards tying first order logic and probability together. And he did it by proposing a particular construction of a single probabilistic theory with probabilities attached to logical sentences. And this idea persisted for quite a long time, that the right way to combine probability and logic was to take logical sentences and then add a probability attached to the front. Okay, and that's the probability of that whole sentence. And he showed with a particular construction that if you wrote down infinitely many logical sentences and attached a probability to each one, then you could get a probability model. But he never actually exhibited such a model or used the logic to represent anything about the world. And fast forward, there were various other papers in the 60s, 70s, and 80s on probabilistic propositional logics, again, attaching probabilities to sentences and then doing various kinds of linear programming to solve the constraints that are applied. Joe Halpern had a somewhat different approach, which is to allow probability expressions as first-class entities within sentences. So, for example, you could write a sentence in his language saying that the probability of one thing is bigger than the probability of another. So it's more likely to rain tomorrow than to snow tomorrow. Okay, and so you could say that in his language. But as with Geifmann's model, each such assertion ends up being a constraint, typically a half-plane constraint on the set of distributions over the possible worlds of the first-order language. And turns out to be very difficult to write a set of constraints that isn't inconsistent. It's very easy to contradict yourself when you write these kinds of sentences without even noticing it, right? And particularly if you start quantifying over the probabilities of various assertions. So another approach was to make sure that when you wrote down sentences in your language, you were necessarily constructing a single consistent probability model. In other words, an assignment of probabilities to each possible world in the logical language. And the way you do that is just to borrow this technique that Bayes nets use to do that. So every Bayes net you write down necessarily constructs a proper probability distribution, because the joint distribution over all the variables is just the product of the conditional distributions in the Bayes net. And so you can't fail, right? You're not writing down constraints on probabilities of possible worlds. You're just composing the joint distribution accordingly. And so you can take that idea and extend it to first order languages without uncertainty over existence and identity. So in David Poole's independent choice logic and Taisuke Sato's prism language, and Daphne Koller and Avi Pfeffer with various kinds of probabilistic description logics, probabilistic semantic networks, and others, you get this, you inherit from Bayes nets this property that you always generate an exact probability model. But those assume unique names, so they assume that any object, any two names in the language have to refer to different objects, and anything that isn't named doesn't exist. So that's the domain closure assumption. I briefly want to mention another branch that took off actually from a paper in 1997, also from Daphne Koller and Avi Pfeffer and David McAllister. The idea came, I think, originally from David McAllister, and he sent me, I think me and Daphne, an email saying, hey, you know, Bayes nets are machines for generating samples, right? Why don't we just use programs instead of Bayes nets, right? If you just write randomized programs, they generate samples, right? The samples of the execution trace of the program. So why can't we use programs as a representation language for probability models? And that led to, after a bit of a delay, then Avi developed his eyeball language, and then later, the group at MIT, Noah Goodman, Josh Tannenbaum, and so on, generated the Church language, which used Scheme as the underlying programming language. And those approaches have been very successful, but they have diverged from the idea of a logic-based semantics, where the probabilities are over possible worlds as opposed to execution traces of the program. So let me go back to this difference between closed universe and open universe. We're going to have a little test. I've sort of given you the answer already, right? Just by saying that. Right. So if I have Father Bill William in my database and Father Bill Jr. in my database, and then I ask the question, how many children does Bill have? right?
At least two. At least two.
Well, someone says at least two. Yeah, and so Herbrand semantics would say exactly two, right? And this is what database systems would answer if you put those two in and then ask the query, it'll say two, right? If you ask a first order logic system, the answer is between 1 and infinity, right? So it's at least one, but William and Junior could be the same person. And in fact, if Bill is Bill Gates Sr., right, and then William is Bill Gates, as we know him, presumably he was called Junior when he was a kid, because his father's also Bill. So they might be the same person. Okay, and this is probably, I would argue, if we're going to capture uncertainty about existence and identity of objects, then we want a probabilistic language with the full first order logical semantics, rather than the Herbrand or sort of database type semantics. So just to illustrate that with a picture, right? I want this difference to be very clear, right? In the closed universe semantics, if I have two symbols A and B and one relation symbol in the language, so it's pretty much the simplest case you could have, then these are the possible worlds, right? So A has to refer to an object A, which is distinct from the object referred to by the symbol B. So in the circles of the worlds, and every world has exactly two objects, and A always refers to A and B always refers to B, right? And then the only thing that changes is, does the relation hold? And in the first world, it doesn't hold of any pair of objects. In the second world, A is related to itself. In the third world, B is related to itself, and so on. And there are exactly 16 of these worlds, right? And they're very homogeneous, right? They only vary in the sort of the matrix that defines the relation between A and B. If we have the open universe semantics, then the standard logical semantics, there has to be at least one object. So if in all the worlds of one object, both A and B have to refer to that one object, right? As soon as you get two objects, then A and B could refer to one of those objects, leaving the other one unnamed, or A and B could refer to two different objects. And then you can also change the relation and so on. But you can also, going to the last world on the bottom right, you can also add many more objects than just two. And at most two of them could be named if you only have the two constant symbols in your signature. And how many worlds are there in the open universe semantics? Well, there's infinitely many, right? And they are sort of much more heterogeneous. And so the difficulty is, how do we find a language that can easily let us write down a probability model that assigns a probability to every one of these worlds such that the probabilities all add up to one? Okay, and so that's the task. Okay, so it actually turned out, with a bit of head scratching while we were trying to figure it out, but once we figured it out, it's like, oh, of course, this was a very straightforward thing, so it helps actually to go back and look at Bayes nets, as Dave McAllister suggested, as sort of sample generating machines, right? They're machines that can produce possible worlds by sampling. So here's a simple Bayes net where this is Yuda Pearl's example, where the alarm goes off in his house, and it could be influenced by a burglary or an earthquake. When you sample in topological order. So you might sample burglary to be true, earthquake to be false, and alarm to be true, depending on the conditional probabilities, which I'm not showing here. And then that's a possible world, right? So in standard propositional logic semantics, I just sampled a possible world, and its probability is the product of the probabilities of each of those sampling events taking place. So what we're going to do is, rather than just adding events like the burglary happening or the alarm going off, we're going to add objects as well. Okay. And so the first kind of statement in our language, it's called BLOG, which we thought was a cute name, stands for Bayesian logic. It turns out to be very useless as a search engine query. The first kind of sentence is what we would normally see in a first order probabilistic language for a closed universe. Namely, we use the machinery of first order logic to give us the ability to quantify over objects. So this is for every house, H, the occurrence of an alarm depends, according to some conditional probability table, on whether there's been a burglary in H and whether there's been an earthquake in the region of H. So now I'm adding a function symbol region to this model. And so with this, I get, I'm now quantifying over all the houses and capturing some regularity in the domain. To put some objects in the world, right? The objects we need for this model are the regions, right? So region of H has to refer to something, so we have to have some objects for it to refer to. And so we'll call those the geological fault regions. And just for simplicity, we'll say the number of those. So this is a number statement, so it has a number sign at the beginning. The number of geological fault regions is uniform between 1 and 10. And the number of houses in any given region R is, let's say, Poisson 50. It doesn't particularly matter for this example. Okay, and so these, when you sample from these statements, right, you generate some particular number of fault regions, and then for each region, some particular number of houses, and that starts to then produce a possible world with objects. And you can intermingle the dependency statements and the number statements. So, dogs could have fleas, but clean dogs have fewer fleas. So the number of fleas on that dog depends on whether it's clean, which is inferred using a dependency statement, and so on. Okay, and just a piece of terminology. The function here, which basically says what region the house belongs to, we're going to call this an origin function, because it's the way that the house traces its origin back to the region that it belongs to. Okay, so with these two kinds of statements, the semantics is actually pretty straightforward. And the key difference from the semantics of first order logic is that the objects are actually, if you like, generation histories, as opposed to just atomic tokens. So a fault region so now we're in semantic land as opposed to syntax land, right? So a fault region, since it has no origin function, right, then this argument here is blank. So it has a type, an origin, and then this is the index. So this is fault region number 3. And then here's a house, and it's the house whose region is fault region number 3, and it's house number 97 in that region. Okay, so that's the object, right? So rather than just naming the objects 01, 02, 03, 04, each object has a complete generation history. And then we can build the random variables of our model, right, from the functions or the predicate symbols. So functions will be random variables whose values are other objects, and predicates will be random variables whose values are true, false. And in any particular possible world omega, right, the earthquake random variable here is indexed by, since earthquakes occur in regions, it's indexed by some particular region. And so this whole thing is a random variable, right? And you can have for every function symbol and every predicate, you can fill in the index by all possible objects or tuples of objects that exist in the world omega to get a random variable. Okay, so when you have a possible world omega, it has to define values for all of these random variables, as well as the number variables. So it's got to say how many objects of each kind there are, and how many fleas each dog has, and so on. And then whether the dogs are clean, whether the houses have alarms and burglaries, and so on. Okay. And the key point here is that the probability of a possible world is then given by the product of the conditional probabilities specified in the model, just as with the Bayes net. Okay. So let me, the reason why is very simple, right? Because there's only one generation path for any possible world. Right? And why is that? it's because each object has its generation history in it. So if you are looking at a possible world and defining it just in terms of, what's true among, with object 1, object 2, object 3, as in first order logic, there might be many different generation paths that could produce the same possible world. And the semantics would have to specify the probability of that possible world as some big complicated combinatorial sum. So in some sense, the semantics would have to do, all the work that you did in homework for discrete probability courses, with counting or all those sorts of things, and binomial symbols and everything else. So this keeps the semantics very, very simple, and then we can write inference algorithms and so on that depend on the semantics. So the key theorem this is Brian Milch's PhD thesis. So I'm leaving out about 120 pages of definitions and proofs, is that every well-formed log model specifies a unique probability distribution that's proper over all the possible worlds that are definable given the vocabulary, given the signature of the blog program. And this is true under some conditions, and these conditions are probably a bit more restrictive than necessary. But you definitely want, at least for simple semantics, not to have infinitely receding ancestor chains. Right? You can have them going, right? You can have infinite descendant chains, but not infinitely receding ancestor chains. And this is something, if you know anything about probabilistic genetics, you know that you get, if you put in certain kinds of mutation probabilities and then go backwards in time arbitrarily far, you get contradictions. So you can only have certain conditional probabilities to get a well-defined probability model. So it's not all expressions finitely evaluable. So you're not going to be able to just write down the rules of arithmetic and ask whether Fermat's last theorem is true, because that's not a finitely evaluable expression. Okay, so let me give you some examples. First of all, citation matching, which is something that Sightseer and Quora, Google Scholar, lots of other services have been doing. And the core computational operation in all these systems is to take strings, which they scrape from the reference list, the bibliography at the end of PDFs that look like papers, to take those strings and decide which strings refer to which papers. And in particular, do two strings refer to the same paper? And so there's clearly existence uncertainty here, because you scrape all these bibliography lists. And often those references are to papers for which you don't have a PDF, right? They're just references, and you don't know which papers exist, right? It could be that everyone makes thousands of typos, and there's really only one paper that was ever written. It's just that we keep spelling it wrong in ridiculously wrong ways, and in fact, there's only one paper that they're all referring to. That's pretty unlikely. But if we look at these two examples, right? Do these refer to the same paper? So I'm not going to do a show of hands here, but when I do this in person, it varies from 10% think it's the same paper to about 80% think it's the same paper. And so it's clearly quite uncertain. In fact, the ground truth is that it is the same paper, right? The second one, even though the authors don't look the same, it's because somebody made a BibTeX error, probably put a comma in the wrong place in the BibTeX file. And so the authors got messed up. The 12th National Conference is what we call AAAI conference, or what used to be the American Association for Artificial Intelligence. So it's the same meeting. Seattle is where it happened. Cambridge is where the publisher is. Notice here in the top one, artificial intelligence, right? That happens a lot because FI is a ligature, and a lot of scraping programs fail to extract the ligature correctly. So you get missing FIs all over the place. So given this very messy raw data, you have to figure out what papers exist, what researchers exist, and then for each paper, what is its real title? Do the best you can to figure out what the real title must have been. Who are the real authors, and then what's the citation graph? Right? So how do we do this? Well, we just write a simple generative model of this world, right? In this world, there are researchers, and so there's a number statement for researchers. And here I've used the order of magnitude distribution. So this is basically 100,000 plus or minus a factor of 10. Okay, so somewhere between, roughly between 10,000 and a million. This is a very common kind of sort of like a log normal, except discrete. And then there are papers, and each author R produces some papers. And if they're a professor, they might produce 100. This is sort of like between 30 and 300, more or less. And if not a professor, maybe they produce 10. So that's between 3 and 30, right? And notice that we don't know professor, right? We don't know who's a professor. In fact, we don't even know who exists, right? But eventually the system should be able to figure out who's a professor and who isn't, at least according to this model. So those are the number statements that talk about the objects that exist, so researchers and papers. And then these are the properties of the objects. So researchers have names, and that could be drawn from a name prior that's developed from a census database. So we actually used a letter trigram prior for generating names, trained it on the census database. And then papers have titles, which we did with a combination of letter and word trigram models from a big computer science paper database. And then we have the citation strings themselves, right? So C refers to a citation string. And so each citation string is referring to some particular publication. So the publication cited, and we don't know which one it is. And a simple model would just say it could be any paper, right? So just uniform from a set of papers, right? And then the citation string has some text. And the text is generated basically from the name of the author of the cited publication and the title of the cited publication. And then that information is put together using some citation grammar. I'm leaving out here like the venue and the date and so on, just for simplicity, so it fits on one slide. And the noisy citation grammar has all kinds of different ways of putting the data together to produce a string. In particular, it has a kind of, I have no idea what the format of this citation is. So it's very robust and it allows for new kinds of citation formats. Okay, so that's it, right? That is a complete citation matching system, leaving out a few sort of boring details, but this is basically it. You just write down the generative model for the world. The data you have is just the citation strings, and then the system has to infer the existence of papers, the properties of the papers, the existence of the authors, which author wrote which paper, and so on. And when we compared it, we did this work in the early 2000s when Sightseer was before Google Scholar. So Sightseer was the top citation engine. And Sightseer conveniently provided some benchmark databases of papers and then we compared our algorithm with Sightseer's to see how many errors the system made in grouping papers together, grouping citations together and saying all these citations cite one particular paper. And so it's a very unforgiving error metric, right? So if you get a single paper wrong, so if you don't include one citation in the set of citations for a paper, or if you include a citation that is to a different paper, then that's a mistake for that paper. And Sightseer on its own data sets was getting 20, between, I guess the best one they had was about 6% and 21% error. And the blog model that I just showed you is about 2 to 3 times more accurate. And later work that Hannah Pasula did got the error rate down very close to 0. About 1% typically the best you can do, because a lot of citations are just malformed. They have an author but no paper, or they have a title but no author, or sometimes they even just have a venue. Okay, I think I'm going to skip over this. This is a model for multi-target tracking with the kind of thing that radar systems do. I'm just go through it very, very quickly, right? In blue, I'm showing you the number statements. So there are aircraft and they arrive with a Poisson distribution in any given time period. And then those aircraft may produce blips. So there are blips that are produced by aircraft, and then there are blips that are produced by nothing, namely those are false alarms. And then there's a motion model for the aircraft, which I'm showing here in blue. So X is the position of the position and velocity of the aircraft at time t. And so this is just a Kalman filter model. And then this is the position of the blip on the screen. If the blip has no source, meaning it's a false alarm, then it could occur anywhere on the screen. Otherwise, it's the usual linear Gaussian Kalman filter noise model. So this captures several hundred papers in the multi-target tracking literature, and gives you, if you have the right inference algorithm, gives you better results than most of the approximate solutions in that literature. We also had fun with Monopoly. We played games of blind Monopoly, where you don't see where your opponent's piece is, and you don't know which properties your opponent holds. The only thing you observe is that you have to pay rent or you get money. And then the system is basically doing a kind of state estimation, so it's sort of integrating all this information over time to get the best picture of the opponent's property holdings and the location of the opponent's piece. It actually works pretty well, surprisingly. The inference was able to handle this quite efficiently, and we're able to test out various kinds of policies for blind monopoly. And this is just showing theta1 and theta2, so the parameters for how likely does it have to be that the other properties in a set are free before you decide to buy the property in a set, right? And then we show that this actually, with these thresholds, the policy plays quite a lot better than the random player. This is a more serious example, nuclear test ban treaty that Annie mentioned. And so nuclear testing has been going on for a while. There have been, as far as we know, 2,055 nuclear tests or nuclear explosions. The first two killed about 200,000 people in Japan, and then I guess no, that's not the first two. That would be the second and third. Killed about 200,000 people in Japan, and then the other nuclear tests just from radioactive fallout have killed about another 100,000 people. And so just for that reason, I think it would be nice to stop doing nuclear tests, but also because without nuclear tests, you can't really have a nuclear arms race. And people have been trying since the 50s to have a treaty to ban nuclear tests. Here's a little picture of a crater produced by a nuclear test. This is in Nevada. This is 12 million tons of earth and rock that was irradiated and dumped into the atmosphere by this test. The largest test was 500 times bigger than this one. So it's pretty serious business. There is a comprehensive nuclear test ban treaty, and there's a global monitoring network for that treaty. And what we do is we collect evidence from 150 seismic stations that are scattered all over the globe. I mean, literally everywhere. Spitsbergen, Antarctica, islands in the middle of the Atlantic and the Pacific, all over the place. So the raw data is all these waveforms. Then the query is what happened, right? So every day produce a bulletin saying these are all the seismic events that occurred in the last 24 hours, their locations, their depths, their magnitudes. And then these are the ones that are potentially man-made based on certain criteria. And so how do we answer this question? We write down a generative probability model in blog, and then we run inference. Okay, here's the generative probability model for the global monitoring system for the nuclear test ban treaty. So again, it's not very big. It took less than a lunch break to write this down. It took a while to get the inference to run fast enough. And my student Nima Arora did heroic work in getting this system up and running, integrating it with the United Nations system in Vienna that's running 24/7. And I'm not going to go through this line by line, but again, you see at the top, right, there's a number statement. Seismic events occur, right? And they occur with a Poisson distribution. And then the third line, right, is it an earthquake? So 99.9% of things are earthquakes, and the rest could be man-made explosions, all right? So I won't go through the rest, but just to say that the system works, so it's about 3 times more sensitive than the previous system that the UN put together with about a decade of work from some of the leading geophysicists in the world. And it also gets more accurate location. So this is a test from North Korea in 2013, and NetVisa is our system, and it gave immediately a more accurate location than on the top left, you see the location estimate, which took 2 days for the world's geophysicists to figure out, pooling their expertise and knowledge and looking at all the data and trying to figure out what happened. And later we discovered that there was a tunnel in this location, so our estimate was pretty good. Okay, so let me talk briefly about inference. We can write the kinds of inference algorithms that are scalable in the sense that they can apply to arbitrarily large probability models. And so those are not the exact algorithms. The exact algorithms for probabilistic inference typically tend to blow up very quickly as your model gets larger, but the sampling algorithms are much more robust. And so we can write sampling algorithms that work, and their convergence, makes, again, some assumptions that probabilities are bounded away from 0 and 1 and so on. But in practice, if you do sometimes you have to do quite a bit of effort in engineering the proposal distributions for the MCMC algorithms. You can get the algorithms to work fairly fast. And the theorems say that for any model, for any query, and for any data, the algorithms will converge to the correct answer. And the ones we have right now, they are, we're at the inference stage of, Davis and Putnam in 1960. So if you remember back, so before we had Robinson and resolution, we did first order logical inference by converting to a propositional model and then running a propositional inference algorithm. So we're sort of in that stage where we construct it's effectively fragments of Bayes nets with grounded random variables, and then run inference on those. And they're dynamic constructions. So when we're running inference on the model for global seismic monitoring, even that model is only half a page. It's generating sometimes hundreds of thousands of random variables. And every millisecond, it's changing what random variables exist and how they're connected to each other, and then continually running inference in that way. So I wish I had a picture of that happening. I should try to make a movie of what that looks like happening in real time, but it's pretty cool. So this general field, so I'm including the branch, which is now quite a bit bigger, the branch that began with the paper from Daphne Koller, David McAllister, and Avi Pfeffer. PPLs have grown very, very rapidly in the last few years. In fact, the growth rate is a little bit faster than the growth rate of deep learning, but we're up to just over 2,000 papers in 2019. And whereas, deep learning is about 10 times bigger than that, but we are catching up. So that's quite promising. But so far, for example, if you want to teach a graduate course on PPLs and you want to, download some nice robust tools, sort of analog of TensorFlow, you're probably not going to be so happy, right? The publicly available blog code is reasonably robust, but is very, very, very slow. There's a group at MIT, Vikash Mansinka has a language called Gen, which is a bit more programmable. You can use meta programming facilities in Gen to guide the inference and make it more efficient. But I think it's a little bit less elegant, and it's based on the execution trace semantics. So I think with real significant engineering effort, we could make a lot of progress. And the efficiency gains to be had from doing this well are enormous, just as happened with logic programming, in the transition due to David Warren's compiler. I actually worked with Prolog both before and after David Warren's compiler became available at Stanford, and it was transformative. And the same kinds of speed ups between 300 and 1,000 come from compiling the inference so that you're producing a model-specific inference algorithm, right? Because the model is always fixed. And if you're doing something like MCMC, right, the computations are extremely repetitive, and all the overhead can be squeezed out and get very, very fast inference. So here's some experimental data. So this is the burglary network. This is actually, it's a 5-variable network. There's 2 more sensor variables below. And you can see that bugs, which is the most widely used BaseNet package, so it's much less expressive, right? Takes 87.7 seconds to do 1 million iterations, whereas Swift, which is a compiled blog language, is 0.124 seconds. Okay, so you've got almost 3 orders of magnitude speed up, even though the language is much, much more expressive, and that's because of squeezing out all the overhead by compiling. I want to mention Infer.net, which is Microsoft's, this is a closed universe PPL, but that's probably the one that has the most engineering behind it. They have a team of 20 or 30 professional compiler engineers who've been developing Infer.net, and they use it for a lot of user-facing real-time probabilistic inference, such as TrueScale, which does, I think, answers about 100 million queries a day on Microsoft's gaming platforms. Let me give you another example of real-time video tracking. So this is the sort of standard state-of-the-art probability model for tracking moving objects in video. And essentially what it says is that the pixel xy at time t is drawn from a multivariate Gaussian, so the RGB value of the pixel. And the properties of that multivariate Gaussian, the mean and the variance, depend on the pixel state. So the pixel state is a hidden variable that says, is this pixel looking at a moving object, or is it looking at the background, excuse me, or is it looking at the shadow of a moving object, right? So there's basically three states: foreground, background, or shadow. But those are hidden variables. And then in the standard model, the pixel state is just sampled at each time step from some mixture weights, which say, 95% of the time things are background pixels, and these can be trained from data and updated continuously over time. But this is the basic model, and this is a generalization of the old-fashioned background subtraction model, which sort of learns the background as an average and then subtracts the background from the current image to leave the moving objects. And that model has various failure modes, and this is a model that fixes those failure modes. But one thing that's weird about this model is that we're saying that the pixel state, foreground, background, or shadow, can change arbitrarily at every time step, right? Whereas if you think about a real video and think about a particular pixel in that video, right? If it's in shadow now, it's probably going to be in shadow at the next time step. In fact, shadow will persist for, some number of frames, 20, 30, 60, 100 frames. If it's in foreground, right, unless the objects are 1 pixel wide, is going to persist in foreground for several time steps. And if it's background, it'll also persist in background state several time steps. So you'd like to have a kind of HMM transition model. And in blog, right, we can just fix that problem, right, just by doing this. Right, we can say, okay, initially at time 0, it's drawn from a categorical distribution, but otherwise, there's a transition model from the previous pixel state at time t-1. Okay, and then this transition model can be learned from data. So a one-line change allows you to bypass an entire PhD thesis and get a better model than the state-of-the-art standard background tracking algorithm. And here's just a demo. OpenCV on the left is probably the most widely used computer vision package in practice. And on the right is the results of the blog model, the one I just showed you, running in the Swift compiler. So it runs in real time on the video and gives considerably better results. See that again. Okay, so none of the weird artifacts that OpenCV produces. Okay, so lots of other stuff to do, right? We would like to be able to learn these models, not just learn the parameters, but actually learn the structure of those models. So this is something that ILP has been grappling with for a long time. If there's, I think there's many valuable things in deep learning, but one thing that I'm particularly keen to understand is how deep learning manages to get feature discovery to work. So it does, in some cases, discover internal features, latent variables that are very useful for inference and decision making. So, and it does it by, as we know, stochastic gradient descent in this big sort of chimney of circuit. And it would be nice, I think, to be able to try to figure out, can we extract whatever is making that work and use it in the context of PPLs to develop new functions, predicates, and so on. And so I think we have to be a little bit more flexible about what we mean by functions and predicates. I think if you come from a logic background, a function is a function. It's a very discrete thing. It's not the same as another function, right? F1 and F2, they're just different, right? In the deep learning world, F1 and F2 are very similar in some latent vector space, if they happen to be nearby in that latent vector space. And so I think we should be able to use those ideas. We also have to be prepared. I mean, another thing about the deep learning guys, they're not afraid to use CPU time, right? I just did a calculation. The time used for AlphaZero, if you trained AlphaZero on a state-of-the-art laptop, it would take you 3.5 million years. Right, so that's a sense of how much computation they're using to do learning because they think it's worth it, and we should think it's worth it too. There's lots of very interesting ideas happening for inference in PPLs, so there's a new type of MCMC which kind of generalizes Metropolis Hastings and seems to make it easier to then do your metaprogramming to design proposal distributions. And describe them at the domain level. So to say, for example, that dirty dogs have more fleas. So if the dog is dirty, generate lots of fleas on it, and that's a good proposal to do, right? So you can use deep learning to speed up the probabilistic inference algorithms by training proposals, seeing which proposals work, and then training on that data to get better at making proposals. Big ideas that are still really waiting for some breakthroughs. I think coarse-defined inference is absolutely crucial for dealing with probabilistic inference in the real world. So coarse-defined meaning that the computations that are going on early on in the inference process should be at an abstract level. So you shouldn't be, if you're doing computer vision, for example, you shouldn't be trying to decide, for each hair on the person's head, exactly where does that hair fall relative to their skull. You should be trying to decide if this is a person or a dog, right? And so that's what I mean by course-defined inference. And there's a lot of evidence that this is what's happening in the human brain and how the human manages to do inference fast enough. Okay, so coming back to my original point, right? We in AI have been assuming from the 50s up until 2010 or so that knowledge is really important, that systems should know things, that the knowledge should be modular, it can be reused for many purposes, and that should have some kind of truth-based semantics, right? And these are religious assumptions, right? We never proved them, right? We just assumed by introspection or because of a philosophical tradition going back thousands of years that this was how to make intelligent systems, right? And I think deep learning is challenging that, saying, well, maybe that's completely wrong, right? Maybe we don't need any of that stuff, right? But so I think the onus is on the community that believes in knowledge and reasoning to actually come up with better explanations, proofs, if you like, for why this kind of architecture for intelligent systems is the right one. And so you could ask questions like, okay, Mr. Deep Learning, this gravity wave detector that the physicists just came up with, and they observed, collisions of black holes more than 1 billion light years on the other side of the universe. Could deep learning do that, right? We know that this was done using a process of learning of explicit knowledge because it relies on centuries of physics, and all those physicists are dead, right? Their knowledge was not communicated as video. The knowledge was communicated as declarative knowledge of physics. And without that, at least it seems to me, there's no chance that the LIGO team could have produced a gravity wave detector. Even something as simple as if I have 2 deep learning systems, right, and they learn something, can one of them tell the other what they learned? Well, how would it do it, right? I mean, maybe it would sort of generate a bunch of natural language and then the other one would read the natural language, but that's exactly what we mean by explicit knowledge. And so this equation, right, that learning is not data goes to knowledge, but it's knowledge plus data goes to more knowledge, right? This is the way we should think about the learning process. And there's just beginning to be some theory on why this is true. So for example, in the theory of reinforcement learning, people are looking at the difference between model-free and model-based RL and showing that sometimes there are these exponential gaps in sample complexity, right? And that's really, I think, the beginning of what could become a fundamental theorem of AI, which is that you should know things, right? We have to figure out exactly how to formulate this as a real theorem, and it's not going to be as simple as that. Because clearly there are worlds where you don't need to know things, right? I don't need to know what's going to happen to my eyeball if a wasp stings my eyeball in order to blink, right? My brain just blinks when the wasp approaches my eyeball, and it's not a knowledge-based process. So there are clearly parts of the world where knowledge isn't necessary, but there are parts where it is. So to summarize, no matter what language you're thinking about, we need ways of capturing the regularities of the universe, and that requires expressive power. And in particular, I don't think circuits have the expressive power to deal with universes that contain many objects. One proposal that I've described is to do it with a combination of probability theory and first order logic. Other people probability theory and programming languages, and there's tons of stuff to do. Thank you.
Thank you so much. I have to say, well, people can ask questions and also type in your questions. But I realized that David has a question or just applaud. I just realized actually I even forgot to introduce the title of this talk, because I saw some version of this talk, right? It was so broad, everything was so beautiful. And I just felt that was, yes, many topics of AI, even think, okay, just probability and first order logic. Sure, that was the particular examples and tools, but it was just so wonderful to see. I love these parts when you say, that hundreds of papers now is on this one slide, and then this whole PhD thesis is just this one thing. It's just amazing. So actually, I remember I was thinking, it wasn't like I didn't have a question. I had so many questions, I didn't know where to ask. But this time, actually, every time I learned something new, of course, you actually even mentioned that I just asked for myself to really learn deeper about these things. And you mentioned about the people using tools, download your systems, the open version, and people improving languages. So I'm sorry, I'm just going to ask my question first, but the people can come up. But anyway, so what is the current state, right? If I want my students to use this, right?
So people have used this in courses. I think Rena Dekter taught a course and used the blog, and it was kind of like I said, right? So students had no problem writing blog models. It was almost, they said it was almost too easy to write down a model of the problem I wanted to solve, but getting Inference to run was really hard, right? So it just, you can use the off-the-shelf generic Inference, but it's going to be very, very, very slow. The inference engine in the public system is, I think it was Brian Milch, probably from 2006. The Swift compiler is really fast. I mean, it's even on a laptop, we can get as fast as 100 million samples per second for Gibbs sampling. So if you actually profile the code, it's spending most of its time inside the C++ random number generator, right? So the overhead is really, really squeezed out.
So it's written in Swift? I thought it was written in Java before.
No, sorry, Swift is the name of the compiler.
Oh, I see, okay.
I know Swift is not, yeah, but so the first system was in Java. Swift is written in C++ and generates C++, which is then compiled. And so what it's outputting is an algorithm that does probabilistic inference for exactly that one model, right? It works for any query and it works for any data, but it's specialized for that one model. And that's what enables it to run so fast. I think, Vikash's group at MIT has put in a lot of work into the Gen language, which is a more procedural-like language, or depending whether you sort of a bit schemy, but basically, or maybe it's closer to Python. But there are now dozens of PPLs. It's easy in principle to take any programming language, even COBOL, right? As long as it has a randomized operator, right? So some way of generating random numbers between 0 and 1, for example, that's enough to then produce probability models that are effectively open universe, because you can say, flip this coin. The coin is heads, generate 2 copies of this data structure, one with these numbers and one with those numbers. Otherwise, only have 1 copy, right? So to me, the drawback of the approach based on distribution over execution traces is that what the inference algorithm is doing is kind of unnatural, right? It's saying, suppose a different choice was made in the execution of the program. And as soon as you make a different choice in the execution of the program, then everything that happened after that choice is invalidated, right? So you sort of throw away that whole section of trace and then sort of start regenerating from the point where you made a different choice. Whereas in blog, what you're doing is just changing something about the world. Like you're saying, suppose that Ben Grossoff and I are actually brothers, even though we didn't know it, right? We just add that brother link into the possible world and then do inference on that basis. So so there's no execution traces, in some sense, introduce an artificial notion of time, right, which is not there in the formal world that you're talking about, right? Or it would actually, if you are talking about the world that does have time, now you have two versions of time, right? You've got time in the world, the dynamical system that you're observing, and you've got time in the execution of the stochastic program, and they may not typically they won't be the same time.
Felix has a question. Go ahead.
Hi, thank you very much. I was just wondering, so the big thing about blog is its open universe aspect, which sets it apart from other statistical relational frameworks. Like the big selling point of those sort of more logic programming based, like probabilistic logic programming, is its support for cycles, at least to the extent that logic programming traditionally supports cycles.
What do you mean cycles? Sorry.
Yeah, so for instance, you have cycles of stratified negation within a logic program.
Like recursion.
Yeah, recursion, but in the Bayesian network that you would have in blog, if you would translate this into a Bayesian network, then you would get cycles.
So that's fine, right? Blog actually, so recursion is not a problem at all, but blog allows cycles, but they're sort of conditionally acyclic, right? And otherwise, you don't have, right, a well-formed probability model at all.
As far as I can see, it was always the sort of magic of probabilistic logic programming, where you could have true cycles that even in an instantiation remain cyclical, but because of this fixed point construction that logic programming is built around, you turn the cycle into recursion, and then it always worked. I mean, I can't be much more precise than that, I'm afraid. I was just wondering if you think this is relevant.
Yeah, I think anything with recursion can, right, so anything that's well-founded can be handled within blog. I'd be interested if there are examples that are more natural to express in a probabilistic logic program than they would be to express in blog. So just, as a general matter, right, we have so much to learn about what is the natural way to write blog models. And to give you one example of something that happened in logic programming, right? It took a while before people realized that you could use these, I think they're called difference lists. There's a way of writing logic programming for handling grammars that is much more efficient than the sort of what you might think the natural way to do things. And and then once you get that, then it becomes the new natural way to write that type of model. And we just haven't had very much practice in writing blog models. We've written 20 or 30. We tried to sort of span a wide range of programs, but I think there's lots more to learn about this. And in particular, I'm very interested in using blog for doing natural language understanding. And example I didn't show here, but with a very simple blog model, right, you can basically say the world has some things in it, don't know what they are, don't know how many they are. They're related in some ways by some relations. I don't know what relations exist. I don't know how many relations there are. But when you want to say something, you take a fact that's true, and then you use a language to express it. So you just write down that model, which is about 11 lines of blog, and then you feed in a few thousand sentences from the New York Times, and it figures out not only what is the language of this text, but also what's true and what relations exist. So it figures out that, yeah, there's a relation which we would call corporate subsidiary. And here are 16 ways that the New York Times describes corporate subsidiariness. For example, it would say, DDB Needham and a unit of Omnicom worldwide, right? And it figures out that that is the corporate subsidiary relation, right? So it's completely unsupervised. And in theory, it could work with a language that we didn't even understand, right? We just put in text from a language and it would figure out what's true and which things are what and what relations exist.
Felix asked a great question.
Thank you very much.
Yeah, exactly. When you started with contrasting this Herban model and this open world, just capture the infinite possibilities. That's really the big difference to make the power and feel supernatural. And even though, in probabilistic logic programming, I was recursion. The distribution semantics, or just give a good semantics, essentially was sort of unfold, right, for a particular problem, how many times. From my understanding, we just had the 2 people who received the 10-year Test of Time awards today for their work on probabilistic logic programming.
Oh, great.
The 2 speeches after one another were what prompted my question.
We're just so lucky to have such wonderful talk, so we can take a little bit more time for informal chats also, because this is actually 15 minutes past the official time. We all know there's official time, but most people still are here. So, but if people feel more comfortable, or I don't know what we can just sort of officially close this and even and just chat for more questions. And I don't know if people.
I think, well, Ben's had his hand raised for a while. So.
Oh, I see. I didn't see it. Sorry. Yeah, Benjamin, please go ahead.
Sure. Great talk, Stuart. I was wondering if you had more thoughts about the potential to hybridize this kind of work with deep learning, where maybe there's some sort of interleaved or modular relationship ultimately in an implementation, but on the way towards that, some kind of theory of being able to kind of extend the representation of knowledge and that's being used for learning to representations of knowledge that maybe would make use of a whole bunch of trained DL models, for example.
Yeah, I think there are many groups exploring that. Facebook is exploring it, Google's exploring it. I'm not sure about Microsoft, but and there are several languages that allow the incorporation of deep learning models. So I mentioned the use of deep learning to train proposals, so that's on the inference side. You can also, represent conditional distributions in the model with any number of different types of deep learning systems. So that's the most common form of integration. Is that the conditional distributions, they can be variational autoencoders, they can be anything, they can be GANs. So there's a number of ways of incorporating deep learning. But as I mentioned towards the end, right, what you would like would be that as the learning took place within the deep learning part of the model, it could sort of graduate to being sort of, a real sentence in the PPL. And so that's the tricky part, right? Because it's a propositional, at least as we understand it now. The deep learning model is this circuit. And how do you get a circuit to graduate to being a sentence of first order logic, right? But ultimately that has to be what happens, right? So it's some sense out of this amorphous sort of continuum of circuit stuff, relational representations, with the machinery of first order logic, particularly quantification of the variables, has to crystallize. And So that's
well, one obvious, I agree that's a major challenge, but there is something fairly straightforward that's an opportunity, it seems to me, which is, there's this problem in the field of DL, which is when is it appropriate to run a given DL model in practical application beyond something that's very close to the setting or kind of, people call it the out of distribution problem, where it was trained. And the learning whether a particular single DL trained model is accurate or appropriate, what kinds of problems it produces in a variety of new settings, that's something that one in principle could sick blog on, right?
yes.
And that would be a kind of meta knowledge learning, not exactly of the DL, but of knowledge kind of extracted from the DL in effect, right?
Yeah, the conditions of applicability. Yeah, if you had a sense of what are the factors affecting the applicability of a DL model, you could certainly write down a blog program to describe that, and you could train the blog program.
Yeah, there's a lot of work on bias, for example, and ML generally, not just DL, where there is a good sense of what are the key, predicates or whatever to then learn a first order representation about, right?
Yep. I think that that could be done. Okay, good plan.
I have a question. Hello.
Sure, go ahead, Veronica.
Hi.
Hi. I'd like to ask you about the idea of generating knowledge from natural language text, which is a wonderful idea. Do you conceive of this process as involving grammar inference, or would it be a little bit like in the deep learning models? Basically,
It would be, yeah, so it would be like grammar inference, except that I think, with all due respect to, generations of linguists, I think they've got the idea of grammar kind of backwards in the following sense, right? What they try to do, and I'm actually going to have to skip out of the meeting soon myself. What they try to do is say, okay, here's a string. Let's see if we can find the structure of the string, right? And so they're going from strings to try to extract structure. And I think instead they should say, here's what we want to say, right? I want to say that one thing happened and then another thing happened, right? How do I do that in this language, right? So start from the knowledge structures and say, okay, for this type of thing that I want to say, what's the linguistic form for expressing it? And there's a branch of linguistics started by a chap, I think he's in Montreal, called Melchuk. He has a whole set of disciples, but it's sort of like, they're pretty much hermetically sealed from the rest of linguistics who think in this more bottom-up way about grammar and what counts as a legal string in the language. And I think that actually writing your knowledge about language in the form, if this is what I want to say, how do I say it, is going to turn out to be easier to learn, more robust. And that's what the example that I just mentioned, in a very simple sense, that's what it does, right? It learns the existence of relations, and for this relation, what are the ways I can say it in English, right? And you can have similar models for entity mentions, right? If here's a person, what are the ways I can refer to the person, right? I can call him Barack, I could call him Barack Obama, Barack H. Obama, President Obama, the president, et cetera, right? There's a lot of different ways, and each one is appropriate in different circumstances, right? And that type of knowledge, I think, is very natural and easy to learn. And then the next step is, can we learn the more general kinds of expressive structures, right? For example, the use of tense to talk about something that happened in the past, right? Here's what I want to say, but I want to say it happened yesterday. How do I say that? That becomes sort of more like traditional grammatical knowledge. But I think we can learn that much more easily within this type of model because we have effective supervision, even in the unsupervised context. So let me explain what I mean by that. I'll give you a simple example, which is not really grammatical, it's more vocabulary. But suppose I said, J.K. Rowling pisal Harry Potter, right? So pisal is a word in Russian. Okay, what does pisal mean?
Graded.
Right, wrote is the author of, right? Right? So from one example with no supervision whatsoever, you correctly learn the meaning of a Russian word, right? And why is that? Was because you already know a fact about the world, and there are clues in the sentence that allow you to map the sentence onto the fact and therefore fill in the gap, right? So people do this all the time. I think this is how we learn foreign languages, how we learn our own languages. It's called bootstrapping. And you can bootstrap grammatical structures as well as just the meanings of vocabulary. And so you get this automatic supervision from unsupervised data as a result.
Yeah, thank you. I guess connecting semantics to syntax is definitely the way to go. I don't think linguists really leave that aside. It's just that computational linguistics has usually stressed another way of proceeding. But
They go backwards, and then
I agree that semantics is paramount
to the structures they extract from the string.
Yeah, the question is, can we completely do away with the structure? Or because I understand starting semantics is a lot.
Just goes the other way, just right. Just
Yeah. Okay. Good. Okay. Thank you very much.
You speak Russian too?
No, I don't speak Russian, right? But that's how I learned that word. Okay.
Yes.
I actually have to.
Yeah, sure. I just want to. By the way, there's one little example Felix gave. I can send you that in the chat. But okay, we can leave this offline. About.
Oh yeah. This is.
Yeah.
I know
yeah. Okay, so we can talk about this.
I just put it on the Slack channel for later reference. I didn't want to delay anyone's dinner or press the point at all.
Sure, okay.
I just put it on the channel for reference.
Sure, thank you. But let's thank Professor Russell again for all these insights. I just can't thank you enough.
Thank you, Stuart.
Okay, so I will have a good evening or dinner or lunch, and I will see the rest of you tomorrow. But thank you so much again, Stuart. I will update you. I would ask you more questions separately.
Thank you very much for inviting me. Thanks everyone for all the questions. Bye-bye.
Bye-bye.